Hello, Namaste. Myself Ankitha Shreya Prasad, and you are listening to along with our NCERT 11th and 12th audio video book presented by ART.SKILL.PASSION. Chapter 12 Atoms 12.1 Introduction. By the 19th century, enough evidence had accumulated in favor of atomic hypotheses of matter. In 1897, the experiments on electric discharge through gases carried out by the English physicist J.J. Thomson in 1856 to 1940 revealed that atoms of different elements contain negatively charged constituents, electrons that are identical for all atoms. However, atoms on a whole are electrically neutral. Therefore, an atom must also contain some positive charge to neutralize the negative charge of the electrons. But what is the arrangement of the positive charge and the electrons inside the atom? In other words, what is the structure of an atom? The first model of atom was proposed by J.J. Thomson in 1898. According to this model, the positive charge of the atom is uniformly disturbed throughout the volume of the atom, and the negatively charged electrons are embedded in it like seeds in a watermelon. This model was picturesquely called plum pudding model of the atom. However, subsequent studies on atoms as described in this chapter showed that the distribution of the electrons and positive charges are very different from that proposed in this model. We know that condensed matter, solids and liquids and dense gases at all temperatures emit electromagnetic radiation in which a continuous distribution of several wavelengths is present. Though with different intensities, the radiation is considered to be due to oscillations of atom and molecules, governed by the interaction of each atom or molecule with its neighbors. In contrast, light emitted from rarefied gases heated in a flame or excited electrically in a glow tube such as the familiar neon sign or mercury vapor light has only certain discrete wavelengths. The spectrum appears as a series of bright lines. In such gases, the average spacing between atoms is large. Hence, the radiation emitted can be considered due to individual atoms rather than because of interactions between atoms or molecules. In the early 19th century, it was also established that each element is associated with a characteristic spectrum of radiation. For example, hydrogen always gives a set of lines with fixed relative position between the lines. This fact suggested an intimate relationship between the internal structure of an atom and the spectrum of radiation emitted by it. In 1885, John Jacob Balmer 1825 to 1898 obtained a simple empirical formula which gave the wavelengths of a group of lines emitted by atomic hydrogen. Since hydrogen is simplest of the elements known, we shall consider its spectrum in detail in this chapter. Ernst Rutherford 1871 to 1937, a former research student of J.J. Thomson, was engaged in experiments on alpha particles emitted by some radioactive elements. In 1906, he proposed a classic experiment of scattering of these alpha particles by atoms to investigate the atomic structure. This experiment was later performed around 1911 by Hans Geiger 1882 to 1945 and Ernst Madsden 1889 to 1970, who was 20-year-old student and had not yet earned his bachelor's degree. The details are discussed in section 12.2. The explanation of the result led to the birth of Rutherford's planetary model of atom, also called the nuclear model of the atom. According to this, the entire positive charge and most of the mass of the atom is concentrated in a small volume called the nucleus, with electrons revolving around the nucleus just as planets revolve around the sun. Rutherford's nuclear model was a major step towards how we see the atom today. However, it could not explain why atoms emit light of only discrete wavelengths. How could an atom as simple as hydrogen, consisting of a single electron and a single proton, emit a complex spectrum of specific wavelengths? In the classical picture of an atom, the electron revolves round the nucleus much like the way a planet revolves around the sun. However, we shall see that there are some serious difficulties in accepting such a model. 12.2 Alpha particle scattering and Rutherford's nuclear model of atom. At the suggestion of Ernst Rutherford in 1911, H. Geiger and E. Madsden performed some experiments. In one of their experiments, as shown in figure 12.1, they directed a beam of 5.5 MeV alpha particles emitted from a 21483Bi radioactive source at a thin metal foil made of gold. Figure 12.2 shows a systematic diagram of this experiment. Alpha particles emitted by a 83Bi214 radioactive source were collimated into a narrow beam of their passage through lead bricks. The beam was allowed to fall on a thin foil of gold thickness 2.1 into 10 to the power minus 7 meter. The scattered alpha particles were observed through a rotatable detector consisting of zinc sulfate screen and a microscope. The scattered alpha particles on striking the screen produced brief light flashes or scintillations. These flashes may be viewed through a microscope, and the distribution of the number of scattered particles may be studied as a function of angle of scattering. A typical graph of the total number of alpha particles scattered at different angles in a given interval of time is shown in figure 12.3. The dots in this figure represent the data points, and the solid curve is the theoretical prediction based on the assumption that the target atom has a small dense positively charged nucleus. Many of the alpha particles pass through the foil. It means that they do not suffer any collisions. Only about 0.14% of the incident alpha particles scatter by more than 1 degree, and about 1 in 8,000 reflect by more than 90 degrees. Rutherford argued that to deflect the alpha particles backwards, it must experience a large repulsive force. This force could be provided if the greater part of the mass of the atom and its positive charge were concentrated tightly at its center. Then the incoming alpha particle could get very close to the positive charge without penetrating it, and such a close encounter would result in a large deflection. This agreement supported the hypothesis of the nuclear atom. This is why Rutherford is credited with the discovery of the nucleus. In Rutherford's nuclear model of the atom, the entire positive charge and most of the mass of the atom are concentrated in the nucleus with the electrons some distance away. The electrons would be moving in orbits about the nucleus just as the planets do around the sun. Rutherford's experiment suggested the size of the nucleus to be about 10 to the power minus 15 meter to 10 to the power minus 14 meter from kinetic theory. The size of an atom was known to be 10 to the power minus 10 meter, about 10,000 to 100,000 times larger than the size of the nucleus. See Chapter 11, Section 11.6 in Class 11 Physics textbook. Thus, the electrons would seem to be at a distance from nucleus of about 10,000 to 100,000 times the size of the nucleus itself. Thus, most of an atom is empty space. With the atom being largely empty space, it is easy to see why most alpha particles go right through a thin metal foil. However, when alpha particles happens to come near a nucleus, the intense electric field, they scatter it through a large angle. The atomic electrons, being so light, do not appreciably affect the alpha particles. The scattering data shown in Figure 12.3 can be analyzed by employing Rutherford's nuclear model of the atom. As the gold foil is very thin, it can be assumed that alpha particles will suffer not more than one scattering during their passage through it. Therefore, computation of trajectory of an alpha particle scattered by a single nucleus is enough. Alpha particles are nuclei of helium atoms and therefore carry 2 units, 2 electrons of positive charge and have the mass of the helium atom. The charge of the gold nucleus is Ze, where Z is the atomic number of the atom. From gold Z is equal to 79. Since the nucleus of gold is about 50 times heavier than an alpha particle, it is reasonable to assume that it remains stationary throughout the scattering processes. Under these assumptions, the trajectory of an alpha particle can be computed employing Newton's second law of motion and the Coulomb's law for electrostatic force of repulsion between the alpha particle and the positively charged nucleus. The magnitude of this force is F is equal to 1 by 4 pi epsilon naught 2e into Ze by r square, where r is the distance between the alpha particle and the nucleus. The force is directed along the line joining the alpha particle and the nucleus. The magnitude and the direction of the force on an alpha particle continuously changes as it approaches the nucleus and recedes away from it. 12.2.1 Alpha particle trajectory. The trajectory traced by an alpha particle depends on the impact parameter B of collision. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. Figure 12.4. An given beam of alpha particles has a distribution of impact parameters B, so that the beam is scattered in various directions with different probabilities. Figure 12.4. In a beam, all particles have nearly same kinetic energy. It is seen that an alpha particle close to the nucleus, small impact parameters, suffers large scattering. In case of head-on collision, the impact parameter is minimum and the alpha particle rebounds back. Theta is equivalent to pi. For a large impact parameter, the alpha particles goes nearly undeviated and has a small deflection. Theta is equivalent to 0. The fact that only a small fraction of the number of incident particles rebound back indicates that the number of alpha particles undergoing head-on collision is small. This in turn implies that the mass and positive charge of the atom is concentrated in a small volume. Rutherford scattering, therefore, is a powerful way to determine an upper limit to the size of the nucleus. 12.2.2 Electron orbits. The Rutherford nuclear model of the atom, which involves classical concepts, pictures the atom as an electrically neutral sphere consisting of a very small, massive and positively charged nucleus at the center surrounded by the revolving electrons in their respective dynamically stable orbits. The electrostatic force of attraction Fe be the revolving electrons, and the nucleus provides the requesting centripetal force Fc to keep them in their orbits. Thus, for a dynamically stable orbit in a hydrogen atom, Fe is equal to Fc. 1 by 4 pi epsilon naught E squared by R squared is equal to mv squared by R. Thus, the relation between the orbit radius and the electron velocity is R is equal to E squared by 4 pi epsilon naught mv squared. The kinetic energy K and electrostatic potential energy U of the electron in hydrogen atom are K is equal to 1 by 2 mv squared is equal to E squared by 8 pi epsilon naught R, and U is equal to minus E squared by 4 pi epsilon naught R. The negative sign in U signifies that the electrostatic force is in the R direction. Thus, the total energy E of the electron in a hydrogen atom is E is equal to K plus U is equal to E squared by 8 pi epsilon naught R minus E squared by 4 pi epsilon naught R is equal to minus E squared by 8 pi epsilon naught R. The total energy of the electron is negative. This implies the fact that the electron is bound to the nucleus. If E were positive, and an electron will not follow a closed orbit around the nucleus. 12.3 Atomic spectra. As mentioned in section 12.1, each element has a characteristic spectrum of radiation, which it emits when an atomic gas or vapor is excited at low pressure, usually by passing an electric current through it. The emitted radiation has a spectrum which contains certain specific wavelengths only. A spectrum of this kind is termed as emission line spectrum and is consists of bright lines on a dark background. The spectrum emitted by atomic hydrogen is shown in figure 12.5. Study of emission line spectra of a material can therefore serve as a typical of fingerprint for identification of the gas. When white light passes through a gas, we analyze the transmitted light using a spectrometer. We find some dark lines in the spectrum. These dark lines correspond precisely to those wavelengths which were found in emission line spectrum of the gas. This is called the absorption spectrum of the material of the gas. 12.3.1 Spectral series. We might expect that the frequencies of the light emitted by a particular element would exhibit some regular pattern. Hydrogen is the simplest atom and therefore has the simplest spectrum. In observed spectrum, however, at first sight there does not seem to be any resemblance of order or regularity in spectral lines. But the spacing between lines within certain set of the hydrogen spectrum decreases in a regular way. Each of these sets is called a spectral series. In 1885, the first such series was observed by a Swedish school teacher, John Jacob Balmer, 1825 to 1898, in the visible region of the hydrogen spectrum. This series is called Balmer series. Figure 12.6. The line with the longest wavelength, 656.3 nanometer in the red, is called H alpha. The next line with wavelength 486.1 nanometer in the blue green is called H beta. The third line 434.1 nanometer in the violets is called H alpha beta, and so on. As the wavelength decreases, the lines appear closer together and are weaker in intensity. Balmer found a simple empirical formula for the observed wavelengths. 1 by lambda. R is equal to R into 1 by 2 square minus 1 by n square, where lambda is the wavelength, R is a constant called the Rydberg constant, and n may have integral value 3, 4, 5, etc. The value of R is 1.097 into 10 to the power 7 meter to the power of minus 1. This equation is also called Balmer formula. Taking n is equal to 3 in equation 12.5, one obtains the wavelengths of the H alpha line. 1 by lambda is equal to 1.097 into 10 to the power 7 into 1 by 2 square minus 1 by 3 square meter to the power of minus 1 is equal to 1.522 into 10 to the power 6 meter to the power of minus 1. That is, lambda is equal to 656.3 nanometer. For n is equal to 4, one obtains the wavelength of H beta line, etc. For n infinity, one obtains the limit of the series at lambda is equal to 364.6 nanometer. This is the shortest wavelength in the Balmer series. Beyond this limit, no further distinct lines appears. Instead, only a faint continuous spectrum is seen. Other series of spectra for hydrogen were subsequently discovered. These are known after their discoveries as Lyman, Paston, Brackett and Pfund series. These are represented by the formula Lyman series. 1 by lambda is equal to R into 1 by 1 square minus 1 by n square. N is equal to 2, 3, 4. Paston series. 1 by lambda is equal to R into 1 by 3 square minus 1 by n square. N is equal to 4, 5, 6. Bracket series. 1 by lambda is equal to R into 1 by 4 square minus 1 by n square. N is equal to 5, 6, 7. Pfund series. 1 by lambda is equal to R into 1 by 5 square minus 1 by n square. N is equal to 6, 7, 8 and so on. The Lyman series is in the ultraviolet and the Paston, Brackett and Pfund series are in the infrared region. The Balmer formula equation 12.5 may be written in terms of frequency of the light, recalling that C is equal to V lambda, or 1 by lambda is equal to B by C. Thus, equation 12.5 becomes V is equal to RC into 1 by 2 square minus 1 by n square. There are only a few elements: hydrogen, singly ionized helium and doubly ionized lithium, whose spectra can be represented by simple formula like
Equations 12.5 minus 12.9. Equations 12.5 minus 12.9 are useful as they give the wavelengths that hydrogen atoms radiate or absorb. However, these results are empirical and do not give any reasoning why only certain frequencies are observed in the hydrogen spectrum. 12.4 Bohr model of the hydrogen atom. The model of the atom proposed by Rutherford assumes that the atom consisting of central nucleus and revolving electron is stable, much like sun-planet system, which the model imitations. However, there are some fundamental differences between the two situations. While the planetary system is held by gravitational force, the nucleus electron system being charged objects interacted by Coulomb's law of force. We know that an object which moves in a circle is being constantly accelerated. The acceleration being centripetal in nature according to classical electromagnetic theory. An accelerating charged particle emits radiation in the form of electromagnetic waves. The energy of an accelerating electron should therefore continuously decrease. The electron would spiral inward and eventually fall into the nucleus. Thus, such an atom cannot be stable. Further, according to the classical electromagnetic theory, the frequency of the electromagnetic waves emitted by the revolving electrons is equal to the frequency of the revolution. As the electrons spiral inwards, their angular velocities and hence their frequencies would change continuously, and so will the frequency of the light emitted. Thus, they would emit a continuous spectrum in contradiction to the line spectrum actually observed. Clearly, Rutherford model tells only a part of the story, implying that the classical idea are not sufficient to explain the atomic structure. It was Niels Bohr 1885 to 1962 who made certain modifications in this model by adding the ideas of newly developing quantum hypothesis. Niels Bohr studied in Rutherford's laboratory for several months in 1912, and he was convinced about the validity of Rutherford nuclear model. Faced with the dilemma as discussed above, Bohr in 1913 concluded that in spite of the success of electromagnetic theory in explaining large-scale phenomenon, it could not be applied to the processes at the atomic scale. It became clear that a fairly radical departure from the established principles of classical mechanics and electromagnetism would be needed to understand the structure of atoms and the relation of atomic structure to atomic spectra. Bohr combined classical and early quantum concepts and gave his theory in the form of three postulates. These are: Bohr's first postulate was that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy. Contrary to the predictions of electromagnetic theory, according to this postulate, each atom has certain definite stable states in which it can exist, and each possible state has definite total energy. These are called the stationary states of the atom. Second, Bohr's second postulate defines the stable orbits. These postulates states that the electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h by 2 pi, and where h is the Planck's constant is equal to 6.6 into 10 to the power minus 34 joule per second. Thus, the angular momentum L of the orbiting electron is quantized. That is, L is equal to nh by 2 lambda. Third, Bohr's third postulate incorporated into atomic theory the early quantum concepts that had been developed by Planck and Einstein. It states that an electron might make a transition from one of a specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted having energy equal to the energy difference between the initial and final states. The frequency of the emitted photon is then given by Hv is equal to Hi minus Ef, where Ei and Ef are the energies of the initial and final states and Ei greater than Ef. For a hydrogen atom, equation 12.4 gives the expression to determine the energies of different energy states. But then this equation requires the radius of the R of the electron orbit. To calculate R, Bohr's second postulate about the angular momentum of the electron, the quantization condition is used. The angular momentum L is given by L is equal to mvr. Bohr's second postulate of quantization says that the allowed values of angular momentum are integral multiple of h by 2 pi. Ln is equal to mvn, Rn is equal to nh by 2 pi, where n is an integer, Rn is the radius of nth possible orbit, and Vn is the speed of moving electron in the nth orbit. The allowed orbits are numbered 1, 2, 3 and so on according to the values of n, which is called the principal quantum number of the orbit. From equation 12.3, the relation between Vn and Rn is Vn is equal to E by root over 4 pi epsilon naught mRn. Combining it with equation 12.13, we get the following expression for Vn and Rn. Vn is equal to 1 by n E square by 4 pi epsilon 1 by h by 2 pi, and Rn is equal to n square by m h by 2 pi whole square 4 pi epsilon naught by E square. Equation 12.4 depicts that the orbital speed in the 19th orbit falls by a factor of n. Using equation 12.15, the size of the innermost orbit n is equal to 1 can be obtained as R1 is equal to h square epsilon naught by pi me square. This is called the Bohr radius, represented by the symbol A0. Thus, A0 is equal to h square epsilon naught pi me square. Substitution of values of h, m, epsilon naught and E gives a A0 is equal to 5.29 into 10 to the power minus 11 m. From equation 12.15, it can also be seen that the radii of the orbits increases as n square. The total energy of the electron in the stationary states of the hydrogen atom can be obtained by substituting the value of orbital radius in equation 12.4 as En is equal to minus E square by 8 pi epsilon m by n square into 2 pi by h whole square into E square by 4 pi epsilon naught, or En is equal to minus me power 4 by 8n square epsilon naught square s square. Substituting values, equation 12.17 yields En is equal to minus 2.18 into 10 to the power minus 18 by n squared g. Atomic energies are often expressed in electron volts eV rather than joules. since 1 eV is equal to 1.6 into 10 to the power minus 19 joule. Equation 12.18 can be rewritten as En is equal to minus 13.6 by n square eV. The negative sign of the total energy of an electron moving in an orbit means that the electron is bound with the nucleus. Energy will thus be required to remove the electron from the hydrogen atom to a distance infinitely far away from its nucleus or proton in hydrogen atom. The derivation of equation 12.17 minus 12.19 involves the assumption that the electronic orbits are circular. Though orbits under inverse square force are in general elliptical, planets move in elliptical orbits under the inverse square gravitational force of the Sun. However, it was shown by the German physicist Arnold Sommerfeld 1868 to 1951 that when the restrictions of circular orbit is relaxed, these equations continue to hold even for elliptical orbits. 12.4.1 Energy levels. The energy of an atom is the least largest negative value when its electron is revolving in an orbit closest to the nucleus, that is, the one for which n is equal to 1. For n is equal to 2, 3 and so on, the absolute value of the energy E is smaller. Hence, the energy is progressively large in the outer orbits. The lowest state of the atom, called the ground state, is that of the lowest energy. With the electron revolving in the orbit of smallest radius, the Bohr radius A0, the energy of the state n is equal to 1. E1 is minus 13.6 electron volt. Therefore, the minimum energy required to free the electron from the ground state of the hydrogen atom is 13.6 eV. It is called the ionization energy of the hydrogen atom. This prediction of the Bohr's model is in excellent agreement with the experimental value of ionization energy. At room temperature, most of the hydrogen atoms are in ground state. When a hydrogen atom receives energy by processes such as electron collisions, the atom may acquire sufficient energy to raise the electron to higher energy states. The atom is then said to be an excited state. From equation 12.19 for n is equal to 2, the energy is minus 3.40 eV. It means that the energy required to excite an electron in hydrogen atom to its first excited state is an energy equal to E2 minus E1 is equal to minus 3.40 eV minus into minus 13.6 eV is equal to 10.2 eV. Similarly, E3 is equal to minus 1.51 eV and E3 minus E1 is equal to 12.09 eV, or to excite the hydrogen atom from its ground state. N is equal to 1 to second excited state. N is equal to 3. 12.09 eV energy is required, and so on. From these excited states, the electron can then fall back to a state of lower energy, emitting a photon in the processes. Thus, as excitation of hydrogen atom increases, that is, as n increases, the value of minimum energy required to free the electron from the excited atom decreases. The energy level diagram for the stationary states of a hydrogen atom, computed from equation 12.19 is given. Figure 12.8. The principal quantum number n labels the stationary states in the ascending order of energy. In this diagram, the highest energy states corresponds to n is equal to infinity. In the equation 12.19 and has an energy of 0 eV. This is the energy of the atom when the electron is completely removed. R is equal to infinity from the nucleus and is at rest. Observe how the energies of the excited states come closer and closer together as n increases. 12.5. The line spectra of the hydrogen atom. According to the third postulate of Bohr's model, when an atom makes a transition from the higher energy state with quantum number Ni to the lower energy state with quantum number Nf into Nf greater than smaller than Ni, the difference of energy is carried away by a photon of frequency VIF such that HVIF is equal to ENI minus ENF using equation 12.16 for ENF and ENI. We get HVIF is equal to ME to the power 4 by 8 epsilon naught by 2 H square into 1 by n square F minus 1 by n square I, or VIF is equal to ME to the power 4 by 8 epsilon naught square HQ into 1 by NF square minus 1 by NI square. Equation 12.21 is the Rydberg formula for the spectrum of the hydrogen atom. In this relation, if we take NF is equal to 2 and Ni is equal to 3, 4, 5 and so on, it reduces to form similar to equation 12.10 for the Balmer series. The Rydberg constant R is readily identified to be R is equal to ME to the power 4 by 8 epsilon naught square H cube C. If we insert the values of various constants in equation 12.23, we get R is equal to 1.03 into 10 to the power 7 meter to the power of minus 1. This is a value very close to the value 1.097 into 10 to the power 7 m to the power minus 1 obtained from the empirical Balmer formula. This agreement between the theoretical and experimental values of the Rydberg constant provided a direct and striking confirmation of the Bohr's model. Since both NF and Ni are integers, this immediately shows that in transition between different atomic levels, light is radiated in various discrete frequencies. For hydrogen spectrum, the Balmer formula corresponds to NF is equal to 2 and Ni is equal to 3, 4, 5, etc. The result of the Bohr's model suggested the presence of other series spectra for hydrogen atom, those corresponding to transition resulting from NF is equal to 1 and Ni is equal to 2, 3, etc. NF is equal to 3 and Ni is equal to 4, 5, etc. and so on. Such series were identified in the course of spectroscopic investigation and are known as the Lyman, Balmer, Passion, Brackett and Pfund series. The electronic transitions corresponding to these series are shown in figure 12.9. The various lines in the atomic spectra are produced when electrons jump from higher energy state to a lower energy state and photons are emitted. These spectral lines are called emission lines, but when an atom absorbs a photon that has precisely the same energy needed by the electron in a lower energy state to make transition to a higher energy state. The process is called absorption. Thus, if photons with a continuous range of frequencies passes through a rarefied gas and then are analyzed with a spectrometer, a series of dark spectral absorption lines appear in the continuous spectrum. The dark lines indicate the frequencies that have been absorbed by the atoms of the gas. The explanation of the hydrogen atom spectrum provided by Bohr's model was a brilliant achievement, which greatly stimulated progress towards the modern quantum theory. In 1922, Bohr was awarded Nobel Prize in Physics. 12.c de Broglie's explanation of Bohr's second postulate of quantization. Of all the postulates Bohr made in his model of the atom, perhaps the most puzzling in his second postulate states that the angular momentum of the electron orbiting around the nucleus is quantized. That is Ln is equal to nh by 2 pi. N is equal to 1, 2, 3, so on. Why should the angular momentum have only those values that are integral multiple of h by 2 pi? The French physicist Louis de Broglie explained this puzzle in 1923, 10 years after Bohr proposed his model. We studied in Chapter 11 about the de Broglie's hypothesis that material particles such as electrons also have a wave nature. C. J. Davison and L. H. German later experimentally verified the wave nature of electrons. In 1927, Louis de Broglie argued that the electron in a circular orbit as proposed by Bohr must be seen as a particle wave. In analogy to wave traveling on a string, particle waves too can lead to standing wave under resonant conditions. From Chapter 15 of Class 11 Physics textbook, we know that when a string is plucked, a vast number of wavelengths are excited. However, only those wavelengths survive which have nodes at the end and forms the standing wave in the string. It means that in a string, standing waves are formed when the total distance traveled by a wave down the string and back is one wavelength. Two wavelengths or any integral number of wavelengths, waves with other wavelengths interfere with themselves upon reflection and their amplitudes quickly drop to zero. For an electron moving in n circular orbit of radius Rn, the total distance is the circumference of the orbit 2 pi Rn. Thus 2 pi Rn is equal to n lambda. N is equal to 1, 2, 3 and so on. Figure 12.10 illustrates a standing particle wave on a circular orbit for n is equal to 4, that is 2 pi Rn is equal to 4 lambda, where lambda is the de Broglie's wavelength of the electron moving in nth orbit from Chapter 11. We have lambda is equal to h by p, where p is the magnitude of the electron's momentum. If the speed of the electron is much less than the speed of light, the momentum is mvn, thus lambda is equal to h by mvn. From equation 12.24, we have 2 pi Rn is equal to nh by mvn, or mvn Rn is equal to nh 2 pi. This is the quantum condition proposed by Bohr for the angular momentum of the electron. Equation 12.13 in section 12.5, we saw that this equation is the basis of explaining the discrete orbits and energy levels in hydrogen atom. Thus, de Broglie's hypothesis provided an explanation for Bohr's second postulate for the quantization of angular momentum of the orbiting electron. The quantized electron orbit and energy states are due to the wave nature of the electron, and only resonant standing waves can persist. Bohr's model involving classical trajectory picture plant-like electron orbiting the nucleus predicts the gross future of the hydrogenic atoms. In particular, the frequencies of the radiation emitted or selectively absorbed. This model, however, has many limitations. Some are: first, the Bohr model is applicable to hydrogenic atoms. It can be extended even to meet two electron atoms such as helium. The analysis of atoms with more than one electron was attempted on the lines of Bohr's model of hydrogenic atom but did not meet with any success. Difficulties lies in the fact that each electron interacts not only with the positively charged nucleus but also with all other electrons. The formulation of Bohr model involves electrical force between the positively charged nucleus and electron. It does not include the electrical force between electrons, which necessarily appear in multi-electron atom. Second, while the Bohr's model correctly predicts the frequencies of the light emitted by hydrogenic atoms, the model is unable to explain the relatively intensities of the frequencies in the spectrum. An emission spectrum of hydrogen, some of the visible frequencies have weak intensity, others strong. Why? Experimental observations depict that some transitions are more favored than others. Bohr's model is unable to account for the intensity variations. Bohr's model presents an elegant picture of an atom and cannot be generalized to complex atoms. For complex atoms, we had to use a new and radial theory based on quantum mechanics, which provides a more complete picture of the atomic structure.
Thank you for being till the end. I hope this has helped you. If so, give thumbs up, like, share, comment, save, download and subscribe. You can support us by following in other platforms. That link is in the description. Well, thank you. See you later. Maybe never.